welcome back, Earth scientists. We've got a new discussion we'll be talking about today, which is really the introduction of geomorphology. This set of the module really talks us through how our landscape has been changed by different processes. And so, what we'll do is we'll introduce this idea of geomorphology as a whole, and then narrow down into the specific areas in which this module will cover. So, nonetheless, let's move on to the first slide, which is, well, what is geomorphology? Well, when you break down that word, geo meaning earth, morph is the change, and ology is to study. So, what we're doing is we're learning how to study in which the ways the earth has changed. So there's different attributes. So I found this little diagram I threw on there, earth, wind, water, ice, and fire. We've already discussed a little bit about Earth and how Earth continues to change due to plate tectonics. We discussed in the previous module about volcanics and looking at fire. So really we're going to take an opportunity within this presentation to discuss wind, water, and ice. So how do those things change our landscape? Well, let's start with wind. So there's a fancy word for this, which is called Aeolian. So wind, Aeolian geomorphology, or studying how the earth changes by way of wind. Now, wind has energy, or the capacity to do work. So that being said, wind is able to erode, transport, and then deposit materials. So wind can erode surfaces and features. It can then take that material and debris and relocate it and move it along its way. And then lastly, it will deposit that material somewhere else. But this brings us back into just, well, where does wind come from again? And simplistically, wind is caused by the uneven heating of our Earth's surface. And because of wind, we're able to then identify very unique and distinct landscapes. So not just extreme weather that can then change the landscape, but looking more at erosion and transportation elements. So these pictures I provided are all things environments that deal with wind. I mean, are there other agents involved? Absolutely, but we can also contribute on most of what we see done by wind. So let's bring in one of the most iconic things that we identify when looking at wind, which are sand dunes. So sand dunes are the most abundant and easily identified features found within areas that are affected by Aeolian processes. So although there's many different types, we're just going to focus on these 6 that we see here in the diagram. But nonetheless, we're going to learn they're pretty much all the same. So what I'd like to start with first is the diagram on the bottom, this guy right down here. So what we have here is a traditional profile or side view of a traditional sand dune development. There are 2 sides. There is the Stoss side. Notice it's the longer word, Stoss, and the longer side. And then we have the lee side, the shorter word, the shorter side. The Stoss side is the side that is hit by the flow of wind. So the wind hits this side, moves the material up, 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 up until it finally falls down on this side. The lee side is sheltered. So you're not receiving any wind right here. The material brings up here to the brink of this crest and then it drops down to its side. What's interesting about this is that if you have just a consistent, not variable amount of sand, very much like a conveyor belt, the sand will take from here, move up to here, and transplant here, and actually cause the dune itself to migrate. Now, if you are in an area that has lots of sand and you continue to gain volumes, this little angle right here, I know you guys are all scared of math, but if this angle increases, so will the dune. But nonetheless, this is a traditional profile. So that being said, all dunes have 2 dominant sides, the Stoss and the leeward side. Now, what really regulates the differences between the 6 sand dunes that you see in the top left-hand corner are 2 variables. One being the wind direction and wind variability, and the second be the supply of sand. How much sand do we have? So we'll start up here. This is the first dune we'll discuss. That first dune, top left, is called a Barken dune. A Barken dune is your classic crescent-shaped dune. We can identify this little angle right here being your Stoss, the sheltered side being the leeward side. But they're very distinct crescent shapes. These are your classic little horns that can develop here. The horns actually point in the direction the wind is flowing, and that's important for people who study these features because maybe you're studying them in an environment that there isn't wind, but you're going to be able to identify the direction which the wind was flowing when these were deposited. Size-wise, these can be very small, maybe just a couple feet. Otherwise, they can be very large, over a mile, in distance across from horn to horn along these crests. So this is dominantly known as a dune that will be available when you have a justifiable or large sand supply and you have one dominant wind direction. Now moving over to the right, we see that this one here has two merging flows of wind. And look at how elongated these dunes have become. This would be like putting Play-Doh in your hands and rolling your hands together and making a long snake. So because of these converging winds, we create these long or linear broken Barcan dunes. We call these linear dunes or longitudinal. Moving again clockwise to the middle right, these are very unique dunes. First thing you notice, there's water involved and there's vegetation to the behind them. These are called parabolic dunes. These are the only times that the horns are actually facing in the same direction the wind is flowing. It creates converging motions. Lots of reasons why. Simplistically, you've got vegetation and water involved. The sand gets wet, so it doesn't operate the same way as it would in a drier environment. But really, if you see there's water and plants, then we know that it has to be a parabolic dune, like a parabola. Again, these are one direction of flow. Moving down here, this is a star dune. This isn't a very good example. We have lots of these in California, especially in the Mojave Desert region area. You have multiple directions of wind flowing, merging all to one place, and you create these very unique sea star or star dune shapes. Again, you have a very large supply of sand, and you'll have maybe wind blowing this way, wind blowing this way, and that way, which leaves these two on the left. So one of them, this one here, is called a transverse dune, and in the bottom left is a barcanoid ridge. So what ends up happening is, in this story, you have Barcan dunes develop. Then let's say that you introduce a new supply of sand. So what ends up happening is that this fills out and turns into a barcanoid ridge. So these are again all your little barcans, but see they're all coalescing. They're all touching, so it's filled into itself. It looks very pointy, right? See, point, point, point. Then maybe you get enough sand that it completely fills in the area where you get these nice, very clean waves. This is called a transverse dune. So you lose the points. So you have transverse, barcanoid ridge, and then a Barcan dune. So these actually can transition back and forth between each other depending on the supply of sand you have. Now, to put this in a perspective of a location you might be familiar with, what about Death Valley National Park? Not necessarily going to be on the exam, but just to kind of put things in perspective. So what's interesting about Death Valley National Park is it's within the greater Mojave Desert. It was first protected as a state park in 1933 by President Herbert Hoover, but it wasn't made into a formal national park until October 31st of 1994. It is unbelievably massive, over 5,300 square miles, and is also home to the lowest elevation at negative 282 feet below sea level. That means it's negative 282 feet below where the ocean is on the beach. You might think, well, then why doesn't ocean water fill it? Well, it's because the way that the mountain ranges are built around it, it has no access to the ocean. It's also home to the Devil's Racetrack, which is the place where rocks can move by themselves. If you've never heard of it, you definitely have to Google it. It's quite impressive. And it's also ranked the hottest and driest national park, and arguably can be the hottest place measured on Earth. The photo I picked there is a national park poster of Ubehebe crater. Really interesting crater. It's a steam volcano that essentially blew up, which allows us to be able to still see the underlying stratigraphy without destroying it like with traditional molten material. So it was mostly steam that built up. Another fun fact, Death Valley, although is one of the hottest and driest places in the world, it used to be a massive freshwater lake known as Lake Manly. It just evaporated very rapidly. Moving into our next process, we'll talk about water or fluvial geomorphology. So we understand by this point that the Earth's hydrologic cycle is much more than evaporation, rain, and snow. We understand the importance of understanding this process, especially since we're experiencing drought in certain areas of the world. Fluvial geomorphology introduces the hydrologic cycle in that if it as a science is devoted to the understanding of rivers, but both in a natural and human induced environment. So we look more than just your traditional evaporation turns into rain and comes back down. We want to look at the process and how these rivers are formed, looking at the depositional material, and also looking at the erosional landscape. So this next slide kind of takes us through a very brief story. So we can see that this larger image here is broken up into three parts: zone 1, zone 2, zone 3. So ideally this is all one progressive river from start to finish, but we can identify each region as its own element. So zone 1 is really considered young and mature. The next one is going to be mature, transition into old age, and then zone 3 would be just your old age. So we're seeing this transition of time, just like with people. And what's interesting with that comparison, going from young, mature, and old age, is that even as humans, we don't associate it with time. We associate it with the development or maturity of that individual. And that's the same thing here, because all rocks operate differently, they erode differently, they build up differently. So we can't say that, oh, just because this environment looks a certain way, it must be X number of years old. It really takes into consideration its development. And the big thing that we see that's different amongst all three of these is going to be its slope. So starting with zone 1, you have your mountain ranges. It's very steep. We find that there's active incision where the river is actually cutting down and creating very steep channels. Once those higher landscapes have been eroded away, we end up with a zone 2 where lower elevation streams merge into a flow, into more of a gentle slope. The valleys begin to broaden, which means you've dug down deep enough that the sides have collapsed and created a very small floodplain. At some point, you continue to dig down to the deepest element in which everything becomes very, very, very wide and not very, very aggressively sloped with a gradient. So at the lowest elevations, a river will meander, meaning that it zigzags back and forth within the floodplain. At a river's mouth, which is where the river ends, it may divide into separate channels, known as a delta system. Things to kind of point out within these features, just to kind of put them out here. These are really unique. These are abandoned channels. At one point, the channel was part of this, but it has since been abandoned because of the widening of this stream. When a stream comes into the main channel, we call that a tributary, because tributaries contribute to the main channel. We can also look at watersheds, meaning this dendritic style of river systems that that are merging or contributing to. We can identify all of this as being part of a watershed. Something that this diagram in the bottom left-hand corner shows that I think is really important is you see the dark blue line that runs within the river. That's called the talweg line. That is the deepest and fastest part of a stream. I often compare it to like driving on the freeway. It's usually associated in the middle of the freeway, in the middle lane. That's the fastest lane. Why? Well, because you have less friction from cars coming on and off the freeway and things of that sort. But what happens when the freeway makes a very sharp turn? Well, imagine about your car. You just went to the grocery store, you have all your food in the back seat, and you make a sharp right-hand turn. The energy forces all of the things in your car to be thrown to the left. In doing so, you will create what we call a cut bank. So looking at this diagram in the bottom left-hand corner, looking at the sinuous, which means that it has curves, following that line, you see the river's making a sharp right-hand turn, but that energy gets forced to the left. Then it moves again to the left-hand turn, but that energy is forced to the right. And you create these pools. These pools are essentially erosion. What it does is it takes the material here, widening this river channel, and then bringing that material and depositing it over here. So this is what we call a point bar. This is also a point bar in here. Point bars are those iconic, you're watching a movie, grandpa's with his grandson, they're fly fishing on a little sandy beach along a river, because this is where the energy is very low in a river, because you see the fastest line, the talweg, is way out here. So fish will wade and kind of hang around here. If they want to leave, they move into the talweg, which is like a current and forces them away. So again, just to put some things into perspective, looking again at like a bigger, putting it together type image. This is the Chaco Canyon diagram. What was interesting about this is that you can see all these different vocab words. So I'll point those out very quickly. Moving at the top where the river is its source, those are your headwaters. So in this diagram, the water is flowing towards us. We can see the talweg is that deepest, fastest part. And, oh, actually, sorry. Now that I'm looking at this, the water is flowing away from us. And notice these little arrows down here. Nonetheless, the water is flowing this way. So this would be the headwaters. This would be the mouth where the river is ending. We can see that the river has now created this flood channel itself. These levees, natural levees, are caused when you have extensive flow and water overflows, like in a flood system, and moves the material onto the side. Here we have the water moving down the channel here. This would be your cut bank. These are your point bars. What ends up happening is these curves become so large, at some point the water may shoot through and cut through it, and when the water cuts through this large, rich meander, this becomes an abandoned channel, which can then become an oxbow. Oxbows are a word for a channel that will become abandoned and will be, essentially a scar on the landscape of showing where the water used to be. Here we have a terrace. Terraces develop when a river system velocity increases. So when the river system increases, it actually causes incision or the river to cut down abruptly, leaving a terrace. So a great example of terraces would be like at Disneyland, where they have the River Terrace Cafe. So you have the restaurant, then there's a step down where the people walk back and forth, and there's one more step down where you then go into the rivers of America. So you have these multiple steps or terraces that have been developed. This diagram here just kind of gives some additional features. This is outlining this whole region, this being a watershed. Here's your source or your headwaters. There's the mouth where a river would end, and here's all your contributing tributaries. Another question that gets asked often is, well, what's the difference between a creek and a stream and a river and a chute and all these different words that we use to identify? And really, it's just vernacular that we use to describe its size. But rivers are the main channel, and then everything else just kind of works its way to a smaller attribute. So you have your main river or channel, then you can have your tributaries, which depending on their size can be very, very small, itty bitty creeks of drainage, or they can also be smaller river systems within themselves. So again, I just saw this diagram was pretty interesting. I found it online, and I thought I'll share it because this kind of puts some of the images together. So again, to put this fluvial aspect into perspective, perhaps you've been to the Grand Canyon. So fun facts, again, the Grand Canyon National Park, it was our 15th national park, 1919 by President Woodrow Wilson. It's nearly 18 miles at its widest and almost 2 miles deep. Oh, gotta fix that guy right there. Almost 2 miles deep within its exposure. So what we're dealing with then is all of that geologic history that had been underlain and not seen for at this point over 1.8 billion years is now exposed. We can see all of this material. So that being said, the formation of the Grand Canyon is really only about 6 million years old, but shows over 1.8 billion years of geologic history. Everything from inland seas to volcanic events to metamorphism. One of the oldest rocks dated in the Grand Canyon is called the Vishnu Schist. It's a metamorphic rock that has these very large, rich garnets, that are within them, and they use the garnets to be able to do the carbon dating to see how old that exposed rock was and how old was it when it was developed, and that's where we got the dates of 1.8 billion years old. So again, really impressive in that sense. The last thing we'll talk about are glaciers, so glacier geomorphology. So I use this because it's in our backyard, Mount Whitney, which is our Everest at 14,508 feet. Mount Whitney is this taller peak here. That's Mount Whitney. These are additional peaks that have names. There's a whole mountain within the Sierra Nevada. There's Lone Pine Peak. There's Mormon Point. All these different peaks that are within that range. But nonetheless, I wanted to point that out because, again, all of that exposed granite was plucked and carved by ice. So glaciers are large bodies of frozen water that develop where the seasonal accumulation of snow exceeds the melting rate. Now, with nearly 3/4 of all of our total fresh water locked up in glaciers and snow caps, we don't really have a lot of fresh water available to us in reservoirs. That being said, our last major ice age was about 2.5 million years ago during the late Pleistocene, and then our last interglacial period or severe cold snap ended 10,000 at the late Pleistocene, at the end of it. So what's interesting about that 10,000 year mark is that seems to be the time in which a lot of our historic mammals had then deceased. We had in California, we had mammoths, we had pygmy mammoths, we had camels, we had giant sloths, we had smilodons, which were the saber-toothed cats. So that it seemed to be really the end of that era of creatures. But nonetheless, we can move into some of these features. This is one of my favorite photos. This is Convict Lake up in along the eastern Sierra. This is really a great example of two features. The one is that this lake, this is a glacially formed lake called a tarn, and that tarn is within what we call a cirque, C-I-R-Q-U-E. A cirque is a amphitheater shape, a bowl-shaped feature that's been carved by ice. So think of it kind of like if you had ice cream and you had your big ice cream scoop and you put that scoop in there and carved out your nice big round piece of ice cream. That carving in that rock would represent the cirque. Cirques are the first place to freeze and then the last place to melt. And the reason it's this round shape is because as water freezes, it expands, and in its process of freezing and expanding, it freezes into the rock material and plucks and carves and removes it all away. So we get this very neat rounded shape. We also can identify other features here. We can see the highest points up here would be considered horns. We can also see blade-like ridges that are kind of off to the sides. They're hard to see in this perspective. We'll identify those as arêtes, and we'll talk more about some of these features. Here's a great example, a cartoon on the left-hand side, and then the drawing on the right that kind of puts some of these words into perspective. Again, glaciers are absolutely massive, and I think it's very interesting to think that within California's history, if you take it way back, we've had obviously glaciation, we've had volcanics, we have earthquakes, we have just about everything within our geologic history, which is really impressive. So again, this image on the left is showing during glaciation. The one on the right is after glaciation. Here we can see this nice rich cirques that have formed, a nice big amphitheater shape, and as the material freezes and accumulates at higher altitude, because of its own weight and gravity, pushes the ice down, 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 down towards where what we call the foot or the terminus of that glacier. These dark lines, you might ask what those are called moraines. So the material that's being scooped out of here and as it gets dragged down, gets pushed to the sides. And same thing here. So these would be a medial moraine because it's pushing the material this way and that way, and they're meeting somewhere in the middle. We can see these high points. These high points are called horns or pyramidal peaks. Often around there we see this really nice blade, this blade-like ridge. There's one here. There's one along here. There's some up in here. Those are called arêtes. Arête, it means blade-like ridge. It's caused because as the cirque and the ice itself, as it's being developed, is pulling that material away. You're left with those really sharp ridges. So, great example here. I'm going to move over to this diagram to the right where we can see what ended up happening after glaciation. Well, what's interesting is traditionally rivers form V-shaped valleys. In this case, glaciers, because as the ice expands, creates these really deep U-shaped troughs. In doing so, we have where things can be truncated or completely chopped off. That's what that means. So spur means a location. Truncation means this whole thing has been cut off. So this is part of an arête system, but the whole end of that arête here would have been cut off. Here we have again, a tarn, which is a lake within a cirque. That water is draining, and as it drains, you see because this has been truncated, it now creates a waterfall. So this valley is hanging above the main trough, which we identify as a hanging valley. This phrase, paternoster lakes, it makes reference into Catholicism, actually, meaning rosary beads, dealing with the Father. So when we find a bunch of lakes that are joined like a bracelet of beads, that's what that stands for. These are a chain of paternoster lakes. Yes, individually they're cirques, but since they're all being joined together, we call them paternoster lakes. So interesting fact, looking at this, so now seeing how big this U-shaped valley is, think about Yosemite Valley and the fact that we have an iconic feature there called Half Dome. Now you begin to question that, well, wait a minute, would have Half Dome been a whole dome? but had that half been knocked off by ice? And I think that you'd be surprised to find that that's the case. Much of the Yosemite Valley itself, it shows the very clear carving or removing of that material. There's some great documentaries on the formation of the Yosemite Valley. In particular, is because it is a very distinct U shape, but it's borderline box shape, and that's because of a thing like this. These are called they're called terminal or end moraines because that's where the glacier had ended. That being said, where the glacier ends, it creates a lake behind it. See this big lake that's developing here? So as that material and fine grained material gets moved by that ice, it begins to deposit those silts and can create a box shape. So that's what ends up happening in Yosemite. It's just kind of one of those fun facts there. So that being said, when looking at glaciers, glaciers carve and erode and pluck and move all this material at a very, very fast pace. But what's interesting about it is it breaks things down to its finest coarse material, being your silts and your clays. So it's really impressive. Um, Granted, most glaciers don't, that we observe today, many of them don't move very fast, but they actually still do. Some can move several meters a day, which means you essentially could watch them move on their own, which is, I think, terrifying, especially when looking at how climate has been changing and seeing how particular glaciers that are still observed on the landscape, especially in the more northern latitudes, how we're seeing that they're moving, you know, 50 to 40 50 to 45 meters per day in retreat, not really in advancement, meaning that they're melting back and breaking away. So when we talk about a glacier retreating, essentially what ends up happening is that because it becomes too warm down here, the ice will actually crack, and when it cracks, this falls off, leaving a new line there. So then it's not really pulling back, like we would think when you say the word retreat. It's more the fact that it's breaking and melting off. uh, Another interesting argument, some people say that, well, we are seeing that the surface of some glaciers is expanding. We're seeing expansion within surfaces of glaciers, and the answer is yeah, in some areas we do, but its density is not the same. So it'd be kind of like, the example I use is like Play-Doh. So if I open a container of Play-Doh and I stick it on the table, I go, well, look, it doesn't cover a lot of area, but it's about 5 to 6 inches in depth. Well, could I, if I had the patience, or maybe perhaps a child can do it because they're good at that, could you spread that Play-Doh over an entire desk? And the answer is yes, you could. You could cover an entire desk with that Play-Doh. Does that mean you have more because it's covering a greater area? And the answer is no, it's not. It's still the same amount, it's just thinner. So, some things to think about within that. Another fun place to kind of talk about more of these features is then after the glacier is gone, what's left behind? So again, these are a lot of words. I'm not asking you to memorize all of these, but to be familiar with some of them. Again, some that can be interesting to talk about. Drumlins. Drumlins are asymmetrical hills made of glacial till. So it's caused as the ice itself is retreating and melting back, leaving these unconsolidated hills of material, or glacial till, T-I-L-L. Another feature we can look at would be kettles. Kettles are caused by when the glacier is moving, it plucks out big pieces of rock or leaves behind big pieces of ice, and it turns into a lake down here on the valley floor. We can see there's additional moraines, meaning that as the glacier advances or retreats, it leaves behind these big piles of debris. When I think of moraines, I think of going to the beach and sticking your feet in the sand. And as you push all of that sand away, you create a big hill. Well, that would be a moraine. You've displaced all of that material. So we can see that moraines can happen at the farthest extent, being a terminal, can happen when the glacier retreats but advances during winter as a recessional, or like a recessional hairline. Or it can even be found that the whole bottom gets a nice little layer of it called a ground moraine. Here's a traditional delta environment because you end up having water that drains underneath the glacier, depositing additional material. Everything beyond the terminal moraines called the outwash plain. Eskers are the remnants of rivers that were flowing underneath the glacier and up top the soil surface itself. Again, when we talk about glaciers, I think it's hard for us to imagine how large they are. Again, to put it in perspective, like I said with a kettle, kettles are caused by either rocks being dislodged or large pieces of ice being deposited and hitting in the ground and making indentation. If you ever have the opportunity or privilege to go to New York, they have Central Park, and Central Park has these massive, massive rocks that have been deposited in that park. Well, those rocks are not from there. Their orogeny is many, many miles away. In fact, these rocks have these very large carvings on them or striations showing the direction in which they were moved. So we end up finding that these rocks have been transported, and we can measure the direction in which they were moved based on the scratches found upon them, and we can date when they were moved, when they were placed, and where their orogeny or where they developed from. So again, a lot of information. I absolutely understand that, but it's a great way to kind of oversee all of these different environments. So we've discussed desert regions very quickly, with predominantly looking at how wind changes the landscape. We also looked at how rivers can change landscapes, and lightly how glaciers can change the landscape as well. Be sure to check out all of the supplementary material within the module itself, and I'm excited. We'll talk soon.